Good morning, everyone, and welcome to our webinar on a practical approach to 4R nutrient management. My name is Tice Masich. I'm the Crops Extension Specialist with the Saskatchewan Ministry of Agriculture and Outlook Saskatchewan, and I will be chairing today's event. CEUs are being offered for certified crop advisors on this webinar. To get credit, you'll need to attend the entire live event, and there will be a QR code at the end of the presentation to collect credit afterwards. If you miss the code, and you have attended the event live, please email us afterwards and we can work with you to get your credit. Before we start the formal presentation, I have a few items to share. Our team of crop extension specialists put on the homegrown webinar series each year. We work out of 10 different regional offices across the province and that are represented on this map. Each office contains a wide variety of specialists who can help you with your agriculture-based questions. If you don't know the phone number to your nearest regional office, then you can contact the Ag Knowledge Center for all agriculture-related inquiries in Saskatchewan. The resource agents managing the Ag Knowledge Center call line will connect you with a specialist in your area to answer your inquiry. In addition to answering agriculture-related inquiries, the Ag Knowledge Center supports clients through the Saskatchewan Crop Reporting Service, the Provincial Rabies Hotline, the Sustainable Canadian Agricultural Partnership, premises identification, and agricultural crown land inquiries. Have you heard of Saskatchewan's AgriArm sites before? AgriArm is a network of producer-directed applied research and demonstration organizations located across Saskatchewan. There are 8 AgriArm sites throughout the province that provide producers with data on sustainable farming practices, technology that is specific to Saskatchewan's different growing environments and soil types. Many of these AgriArm sites host field days each summer and take turns hosting Crop Diagnostic School each year. This year, Crop Diagnostic School will be at the Northeast Agriculture Research Foundation by Melfort, Saskatchewan on July 24th and 25th. Keep watching our social media pages for registration details in the coming months. Lastly, we want to ensure that everyone is aware of the funding available through the Sustainable Canadian Agricultural Partnership. You can reach out to your local agricultural program specialist to find out what funding you may qualify for. For today's webinar, we have 2 great speakers presenting on 4R nutrient management and stewardship. First up is Blake Weiseth. Blake grew up on a mixed grain farm and livestock farm near Shaunavon, Saskatchewan. He holds a joint role of applied research lead at Glacier Farm Media Discovery Farm and research chair at Saskatchewan Polytechnic, and is currently pursuing a PhD in soil science from the University of Saskatchewan, working under the supervision of Drs. Jeff Shano and Jane Elliott. He is a professional agrologist with the Saskatchewan Institute of Agrologists and was recognized by the institution as the 2024 Outstanding Young Agrologist. His research focuses on evaluating agricultural management practices and emerging technologies for their ability to optimize water nutrient use efficiency while limiting nutrient losses in runoff water. The second speaker we have today is Lyle Cowell. Lyle is the Senior Canadian Agronomist with Nutrient Wholesale and supports agronomy and sustainability of the nitrogen, phosphorus, potassium, and sulfur fertilizers that are manufactured by Nutrien. His previous career was with the regional agronomist, as a regional agronomist in Northeast Saskatchewan, where he extended agronomy research to the farm gate. Lyle has always had the goal of connecting good research, sound soil fertility principles, and agronomy extension to honest farm gate advice. We have a few housekeeping notes to keep in mind during this webinar. Each speaker will give a 45-minute presentation followed by a 15-minute question period after each speaker. If anybody has any questions during the presentation, you may type them in the question box at the bottom right-hand side of your control panel. Your question will remain anonymous and it will only be sent to me. During the presentation, you will be muted so that we can ensure that there's no feedback or interference with the audio. The entire session will be recorded, so if you miss anything or wish to rewatch any of the presentations, you'll be able to do so. Recording links will be sent out in the next few days in a follow-up email. An evaluation will pop up at the end of the webinar this morning. Please fill out this evaluation as it helps us determine what topics you want to learn more about and help us prioritize research needs in the future. And with that, we'll get started. Blake, go ahead whenever you're ready.
Great, well, thanks very much, Tice, for the introduction. Just bear with me as I share my slides here. All right, I think it looks like everything is up on the screen. I just want to Tice, can you chime in and see if my slides are up on the screen? I cannot see the slides on my screen.
Yep, for sure. The slides appear on my screen, so I think you should be good to go, Blake.
Okay, just wondering how to advance the slides because I cannot see them. Okay, oh, maybe I minimize this. Sorry, folks. Okay, there we go. I think we're in business now. All right, so thank you very much for the introduction, Tice. It's great to be here for this webinar session. And I really just want to give a shout out to the Ministry of Ag for assembling this Crops Winter Webinar Series. Today, of course, we're going to be in the theme of a practical approach to foreign nutrient management. And I'll be talking about specifically dialing in the 4 Rs of phosphorus stewardship with technology. So really drawing on a couple examples of the work that I'm doing in the field, but specifically starting, I guess, with the question of why we should care about 4R nutrient stewardship and dialing in these 4 Rs of nutrient stewardship. And for me, really, it's about building the case for site-specific phosphorus management. So I'll be speaking specifically to 2 of my research studies from my PhD work under the supervision of Drs. Jeff Shano and Jane Elliott to make this case. Of course, there are different technologies now that we have available to us, but there needs to be utility of these technologies. And if there's no utility, then there isn't a point in using these. So really just making this case of first, we should care about that site-specific phosphorus management. It does seem that there's a bit of a lag in advancing my slides, so I think maybe it is best that I shut off my webcam just to hopefully help with that lag. But I do want to acknowledge first at the outset that the work that I'm describing was conducted on Treaty 6 territory and the homeland of the Métis, and that's as well where I'm delivering this online presentation from today. By way of introduction, it's important to look at the phosphorus cycle. So I put it up on the screen here, not for the sake of boring you folks to tears here this morning on Wednesday morning, but really just to highlight the complexity of the phosphorus cycle. I think we often think of the nitrogen cycle as being one that has some complexity associated with it, but certainly it's true for the phosphorus cycle as well. We know, of course, there's oftentimes a lot of phosphorus, total phosphorus in the soil, but really what we care about is what is available in that soil solution. So that's the inner circle on this figure on the screen here. And this is composed of inorganic ions that are largely available for the crop uptake. And so ultimately, we think of inputs into this system, notably, of course, fertilizer and manure addition being important components of that. We have some hydrolysis or conversion of organic phosphorus forms to inorganic forms, and then importantly, transport or losses from the system. So leaching, typically not that important in the semi-arid environment of the Canadian prairies here, but runoff is an important component, and that is something that I'll be touching on in this presentation today. And then we have a number of internal cycling within this agroecosystem phosphorus cycle. So microbial mineralization and immobilization, of course, what's being taken up by the plant and released through decomposition. And then chemical processes, which are temporarily pulling that phosphorus out of the soil solution and causing it to be fixed. So in my work, if we want to really understand, the amount of phosphorus that's available in the soil solution, what's available for crop uptake it's important to be measuring these different pools. And so that really informs a lot of what I do in my research, is tracing the fate of the phosphorus through that plant, soil, and runoff water system. Now, by way of introduction, the ability to predict the fate of fertilizer phosphorus as influenced by management is important to meet our agronomic and environmental objectives of really maximizing crop utilization of that applied fertilizer. Really, this is the goal for us as agronomists and other stakeholders. We want to maximize that use efficiency of that fertilizer. We want it to be taken up by the crop and to limit losses from the system. We also know that 4R nutrient stewardship practices influence that availability of phosphorus for crop uptake, as well as export in snowmelt runoff water. And this is important because the spring snowmelt represents the major hydrologic event on the Canadian prairies here. We know that snow typically amounts to about 30% of the annual precipitation, but it translates into greater than 80% of the annual runoff. And we're experiencing the runoff, of course, right now across much of Saskatchewan. Now, despite the familiarity of these 4Rs of nutrient stewardship, what we determine as the right combination of these management practices is often less well known and may not account for some important driving factors of soil, site-specific soil and landscape characteristics that I'll be talking about today. Now, the objective of my research really is to evaluate what I call both the agronomic and the environmental performance of phosphorus fertilizer sources as influenced by interactions amongst the 4Rs of nutrient stewardship and localized landscape and soil characteristics. And so a bit of a model that I have conceptualized when I think about, how do we evaluate both the agronomic or environmental performance of phosphorus fertilizer, I suggest that it's a function of interaction amongst a number of different factors. So as you can see in the diagram on the bottom of the screen here, of course, the 4Rs of nutrient stewardship, that is the right source, the right rate, the right placement method, and the right time, are important. But these also interact with how these practices are applied at the individual farm level, particularly with respect to crop choice. So of course, we know that we would likely fertilize our cereals different from our oil seeds, different from our pulse crops. And there may also be limitations with respect to the equipment that we're using at the farm level that influences the rates and the timing of fertilizer products that we're applying. Now, I think traditionally this is where we stop insofar as evaluating the performance of a fertilizer product. And what I suggest today is the need to bring in this third component, which is the localized landscape and soil conditions. So the first study that I'll be describing today is a 3-year crop rotation study that was initiated in the spring of 2021, where wheat was the crop of interest, followed by pea in 22 and canola in 2023. And it was established at 3 field sites in Saskatchewan. So 2 of the sites were located in the brown soil zone, so the bottom red star that you can see on the soil map. And each of the 3 sites are meant to represent a unique landform complex position. So in the brown soil zone at this site here, we had 2 sites in the same field having a common management history. One is on a upslope position, a water shedding position, and the second is just down the landscape in a water collecting low slope position. So those sites I'll refer to as CB upslope and low slope. And then we had a third site in the dark brown soil zone at the location of the top red star near Langham, Saskatchewan, on relatively level topography, and we call that the Langham mid-slope site. Now, the study was set up as a 3-way factorial treatment structure, so we're looking at 3 factors of source, where we had 8 phosphorus fertilizer sources and an unfertilized control being applied at both a low and high rate of 20 and 40 kilograms P2O5 per hectare, and applied either in a sideband or spring surface broadcast. Now, I include this photo on the screen here, which shows the relative location of these 2 sites at Central Butte. So you can see quite closely located together geographically, but we do see this aspect of landscape where you have the upslope site in the foreground and then the low slope site in the background. And you can even see the difference in relative maturity of this wheat crop at this site. Both of these sites were seeded on the same day, but of course we see this low slope site delayed in maturity relative to the upslope site. I also want to provide some baseline soil characteristics about these sites. So what you can see in this table here, this is from samples that were collected in the spring of 2021, so prior to the initiation of any of the treatments. So I have various soil parameters listed across the top of the table, and then each of the 3 sites along the side and the various depth increments. So a couple of things I want to draw your attention to. First of all, we see in terms of the plant available phosphate, very consistent across the 3 sites, and each of the 3 sites we would consider deficient in plant available phosphorus at the start of the project. But we do see some noticeable differences across the sites. Importantly, this increase in organic carbon as we move from the upslope to the low slope position at the Central Butte site, and then some differences in pH and electrical conductivity, particularly seeing elevated levels in these 2 parameters at this Langham mid-slope site with the elevated pH and slightly saline conditions. So this Langham site does represent a bit of a marginal site in terms of some of its soil characteristics as it relates to water availability and nutrient availability. So keep this in the back of your mind. We'll draw on this later as we go over some of the results. I include this table here of the phosphorus fertilizer sources. You can see them listed by name and then chemical analysis. So within the fertilizer sources, I have the name listed and then the acronym in brackets, which is how I'll refer to it in the tables and figures. Now, importantly, within these phosphorus sources, we do see a range of solubility, and that's important because the plant availability of a fertilizer phosphorus source is influenced by its solubility. And so if we think of the spectrum here, we have sources such as rock phosphate, which is poorly soluble. Intermediate within that, we have a source such as struvite, number 8 listed on the table here. And then on the other end of the spectrum, source number 4 is the relatively available monoammonium phosphate. And of course, monoammonium phosphate is the most commonly applied phosphorus fertilizer source here in Saskatchewan. Now, another source that I want to just briefly highlight for you today is this polymer coated MAP. So what that is it was a pre-commercial product that I had access to through Jeff Shano's lab. And what it is MAP with a polymer coating. The idea is to slow the dissolution of that MAP granule and prevent fixation to the soil components. So a bit of a slow release phosphorus fertilizer source. Within the chemical analysis, you can see certainly a range of nitrogen content across the sources, as well as sulfur into the sources, but basal applications of nitrogen and sulfur were added to balance across the treatments. And before jumping into the results, I always like to frame it within the context of the growing season conditions. So we have 2 of the sites represented on the screen here and showing mean temperature and total precipitation over the growing season by month from May until August and within each of the 3 site years. So importantly, what we see is if we look at these precipitation totals, certainly below our historic 30-year averages, which is to say experiencing some drought-like conditions at these 2 sites over the 3 years of the project. All right, so jumping into the results now. So this is the 2021 wheat yield at the Central Butte upslope site. We're looking at the factor of fertilizer source. So you can see the sources listed across the x-axis and then yield in kilograms per hectare across the y. We do see a significant influence of source in this year where we see significantly higher yield from the application of ammonium phosphate sulfate fertilizer compared to the control treatment. Now, when we move to the low slope site, the first thing that I want to point out is you'll notice if you look at the scale of the yield, we're seeing much greater yields at this low slope site relative to the upslope site. So what I did, these red lines that you can see on the blue grain yield bar graphs, those red lines represent within each of the sources the yield that was measured at the upslope site. And so you can see across all the sources, we're seeing twofold or greater yields at this low slope site relative to the upslope. So I guess that begs the question, certainly we see different yield potential at these 2 sites. Should we be managing them differently, or can we see that there's different performance of these 4Rs at these 2 sites? While there wasn't a statistically significant influence of source, we did note that the greatest yield was observed from these sulfur-containing sources. And if we move to the Langham site here, again, we see a different scale in terms of the yield, lower yields at this Langham site, as I'd mentioned, as a function of these saline conditions, as well as the drought magnifying that impact in 2021. Now, in terms of another measure of agronomic performance, we want to know where the phosphorus is residing following harvest. So this is post-harvest soil test phosphorus results. We have, just to walk you through this table, the 3 sites represented and then showing 2 soil tests. So the grouping of numbers on the left is modified Kelowna extractable P. This is a common soil test phosphorus measure. And then on the right, we have anion exchange resin P. So this is a measure of exchangeable soil phosphorus. And if we look at the factor of source, what we can see is generally we are seeing an impact of source in terms of the residual soil P. So if we look at the upslope site, we're seeing we have greatest residual P from the ammonium phosphate sulfate treatment. At the low slope site, we see it from the polymer coated MAP, and at the Langham site from the MAP plus elemental sulfur. And I do also want to point out that if you look at the Langham site, we see the lowest residual P at this Langham site compared to the other 2 sites. And I'll speak to that a little bit later in terms of what we're observing in that situation. If we look at the factors of rate and placement method, so you can see the rates listed here, and generally we do see a significant influence of rate. So as we would expect in this first year, we're seeing greater residual P from that high application rate relative to the low rate. And in terms of placement, generally not a significant influence. However, from the 2 placement methods, we're seeing greater residual P from this sideband application compared to the broadcast. And I think this really highlights what we know to be true for best management practices for in-soil placement of phosphorus on deficient soils. Get that phosphorus in the soil near the rooting zone and preserving that in a plant available form. Now, in terms of environmental performance, how we measure this is through a snowmelt simulation experiment, which is what you can see in the image in the video on the screen here. So from each of the plots where the fertilizer was applied at the high application rate, I collected what I call an intact soil slab. So this is a 3-dimensional volume of soil. Really what we're trying to do is retain that soil structure of how it was located within the field. So it's placed in this aluminum tray. We can take that back to the lab and then freeze it and then do this snowmelt simulation experiment. So important within this, we do want to capture these landscape conditions, particularly with respect to the slope. And so we're able to manipulate that slope of how those slabs are situated within the snowmelt experiment. We set them on this slope, and then we can add a predetermined amount of snow to the top. Under controlled temperature conditions, it's allowed to melt. That melt water is going to interact with the very shallow surface soil layer, that effective soil surface, as well as move laterally across the soil and then into the sample pail where we can collect a sample for analysis. And this is the results of what we see from this simulation. So what we're looking at here is the factor of the fertilizer source and reporting soluble reactive inorganic phosphorus. So this is dissolved plant available phosphate along the y-axis. So a couple things that we can see is we can look at comparing the concentration of the phosphorus in the runoff water within a given source across the sites. And so as an example, in this MST treatment, we see significantly lower losses from the orange bars, the Central Butte low slope site, compared to the gray bars of the Langham mid-slope site, which is to say then there is something about this aspect of site that is driving the losses of phosphorus in the snowmelt runoff water. We can look within each of the sites, and so starting with the blue bars for the Central Butte upslope site, we can see for the sources circled on the right, significantly higher concentration in the snowmelt water compared to the control treatment. There wasn't a significant influence for the orange bars of the low slope site. However, at the Langham site, the gray bars, we do see a significant effect as well, where we're seeing significantly higher concentration from these two sulfur-containing sources. And interestingly, if we look at rock phosphate across each of the three sites, or struvite for the low slope and the Langham site, we see losses not significantly different from the control where no phosphorus was applied. Now, jumping ahead to 2023, so the last year, the most recent year of this study, and looking at the canola yield at the upslope site. So in this instance here, we're reporting the treatment combination of source by placement method. So you can see those treatment combinations across the x-axis. Just to walk you through how I'm denoting these treatments. So as an example, you can see APS, which is ammonium phosphate sulfate, followed by either SB for sideband or B for broadcast, and then yield in kilograms per hectare. So we didn't see a significant influence of the treatment combination at the upslope site. When we moved to the low slope site, reporting the same treatment combinations, and again, just wanting to highlight this difference in the yield at this low slope site compared to the upslope. So I've reported the upslope yields again for these red bars, these red lines across the blue grain yield bars. We did see a significant influence of the treatment combination at the low slope site, in particular, seeing the highest yields and a significantly higher yield from MAP, or the polymer coated MAP, being broadcast compared to the control treatment. And then finally, the Langham mid-slope site, where we do see this time, in this instance, severely reduced yields as a function of the third successive year of drought conditions at this site. But that said, we can see the highest yields measured were from those where we had these sulfur-containing sources. Looking at the residual soil test phosphorus, so we have same table to what I presented earlier, where we have the three sites and the two soil test measures, and looking at the factor of source for starters. In general, we are continuing to see a significant influence of source. So at the upslope site, monoammonium phosphate is coming through amongst the highest residual soil P. At the low slope site, we are seeing this polymer coated MAP having the highest phosphorus supply rate. So I think what we're observing here is at this low slope site with improved soil moisture dynamics, really this polymer coated MAP is starting to do its job, where it's breaking down with the improved soil moisture conditions and then responding in terms of a higher phosphorus supply rate at that site. And then for the Langham site, we're seeing the highest residual P from the MAP plus elemental sulfur. The other thing that I do want to point out is for, excuse me, for the rock phosphate, we see after 3 years of fertilizer application at relatively high rates across the sites and soil test measures, we see residual P not significantly different from the control treatment where no fertilizer had been applied for the 3 years. And in this instance, highlighting the Langham site, so while in 2021 when we saw the lowest residual P at this site, in this instance we're seeing highest, and this is the evidence of this successive years of fertilizer application coupled with a relatively poor yields from the drought, and we're really seeing the residual P being loaded up at this Langham site. So it appears by this third year we're witnessing a bit of a threshold in terms of the residual P. Looking at the factors of rate and placement, we're continuing to see this significant influence of rate, whereas we would expect higher residual P from the high application rate relative to the low. And for placement, it's interesting, not a significant difference, but in terms of absolute values, if you look at the sideband versus the broadcast, now in this third year, we're seeing the highest residual P from the broadcast application. So I think this also reflects 3 years of the application of the broadcast, really mitigating some of this influence of placement that we saw in that first year. And this makes sense when we look back at the 2023 yield at this low slope site, where we saw the highest yield reported from 2 of the treatments where the fertilizer was broadcast. The last thing that I did for the 2023 soil slabs that I removed from the field, similar to 2021, is I had a plant root simulator probe inserted within the soil slab to measure the phosphorus supply rate. So you can see, looking at the treatment combinations of source by placement method, and then reporting phosphorus supply rate. So a couple of things that we can notice here. First of all, for a number of the treatment combinations, we do see the highest supply rate from at the Langham site, which agrees with the high residual P that we witnessed at this site, as I previously showed. We can look at the significant influence within each of the sites. So for the blue bars, the Central Butte upslope site, seeing a greater supply rate from certain sources compared to the control. We can see this also at the Langham site. And looking now for the results in the runoff water from the 2023 snowmelt simulation, as we saw in 2021, again, within certain sources, seeing the significant influence of the site itself. So as an example, for the ammonium phosphate sulfate treatment, significantly lower concentration in the runoff water at the low slope site compared to the upslope or the Langham site. Within sites, we can see, so for the upslope site, significantly higher losses from certain site sources compared to the control. Within the low slope site, we also see significantly higher losses from certain sources compared to the poorly soluble rock phosphate. And for the Langham site, significantly higher concentration from these sulfur-containing sources compared to the control. And as we saw in 2021, in 2023, we also see from these relatively low solubility sources of rock phosphate and struvite, losses not significantly different from the control. So I recognize that a lot of rock phosphate isn't likely applied at a commercial scale here in Saskatchewan, but for something like struvite, this may be a source where we're getting acceptable yields, but having losses not substantially different from when no fertilizer was applied. So to sum up what we saw over this study, we saw that the wheat yield was impacted by the source or the source by rate interaction. And we know that the plant availability of fertilizer phosphorus is influenced by its solubility. So this variation in soil moisture dynamics likely impacted phosphorus uptake. And we saw that in terms of the differing yield response at the sites. There's some interesting trends in terms of the phosphorus sources. So as an example, the ammonium phosphate sulfate and MAP plus elemental sulfur consistently seen this effect of high yield, high residual P, and high phosphorus uptake. And this is to contrast the polymer coated MAP and rock phosphate, where generally we're seeing low yield, low phosphorus uptake, and low residual P. And at the Langham site, consistently is seeing this effect of low yield, low phosphorus uptake, and low residual P, especially in the first 2 years of 2021 and 2022. And in terms of just thinking about what's going on at this Langham site, I think we can, it helps to explain it when we look at this figure, a classical figure here showing the distribution of soil phosphorus forms as a function of pH. So to walk you through this figure, we have a range of pHs listed across the x-axis, and then the y-axis, the distribution of the soil phosphorus forms. So you can see the pool on the bottom, relatively available phosphates across the range of pH is low distribution. A low amount of that total phosphorus exists in that pool. You can see it peaks around pH of 6.5, but as we increase it to pH 7 or 7.5, we see a sharp drop off in the residual, in the available phosphorus, and much of it predominating as calcium phosphates in a plant unavailable form. So if you think of this Langham site where we are at pH 7.6, really low in terms of that availability of the phosphate, and the highest yields were often reported where these sulfur-containing fertilizers were being applied. And so perhaps this ability to just modify that pH in that rhizosphere to improve the availability of the phosphorus. And so this is a challenge that we see with phosphorus fertility on high pH soils. And maybe some folks on the webinar here with high pH soils are consistently seeing low available phosphorus coming back on soil test results. And previous work has shown that sulfur-containing fertilizers, particularly the elemental sulfur, has that ability to improve the solubility of the fertilizer due to that acidifying effect. So just walking through some of the agronomic performance. So we saw that the fall 2021, the soil exchangeable and soil extractable and resin exchangeable P was significantly influenced by source at 2 of the sites. And we saw a significant influence at all sites in 2023. The MAP containing sources with and without sulfur tended to have the highest residual P. Canola yield was influenced by this fertilizer source by rate by placement interaction at the low slope site, but at the upslope site, grain and straw yield are not significantly influenced by source, rate, or placement. And this agrees with previous work from Regis Karamanos that has shown the inconsistent yield response of canola to phosphorus application on soils with greater than 15 ppm Olsen P. So just pulling a table from Regis Karamanos' paper, which shows the percentage of a number of field trials that showed a response to phosphorus fertilizer application when the soils were greater than 30 pounds per acre, which is often indicated as a sufficiency level. And so you can see within each of the crop types, as we increase that fertilizer application rate, really decreasing are those percentage of the trials that responded to that fertilizer P. In terms of what we saw in the runoff water, we saw that the concentration was influenced by source at the upslope site and the Langham site in 2021, and in 23, source had a significant influence at all 3 sites. Now, we did see again this influence within certain sources. The concentration significantly differed across sites, and if we average it across all sources, we saw that the concentration increased from the low slope to the upslope to the Langham site, and really this agrees with what we've observed, that crop removal, soil properties, and landscape position appear to be significant driving factors in nutrient transport. So a bit of a take-home message from this study that I'm seeing so far emerging is, how can we implement strategies to maximize that crop utilization of phosphorus, and then by default to limit losses in the runoff? How do we look for efficient systems? So this now causes me to jump into the second study that I'll be describing, which is really application of these 4R stewardship practices at the farm level. And so to provide a bit of a context on this study, it really includes 2 different phases. The first is the implementation of a wetland consolidation project working in close consultation with the Water Security Agency. So what you can see in the image on the left is a satellite image of my field site near Langham, Saskatchewan. The red polygons denote the boundaries of 8 ephemeral wetlands, or you could call them basins or sloughs, within this field site. And then the teal lines represent a network of surface ditches that were constructed to channel the water from each of the basins to an approved adequate outlet. So 3 of the basins on the west side channel that runoff water to a permanent wetland in the middle of the property. And then following this consolidation project, we implemented a 3-year field study, which is meant to assess the performance of different cropping and fertilizer management practices for their ability to maximize utilization of phosphorus and limit losses. And so in terms of the treatments, we had a control, which is an annual grain crop managed with fixed fertility and minimum tillage. The second treatment was light residue management with tillage. So the idea behind this is recognizing that crop residue left on the soil surface can release appreciable amounts of phosphorus in the snowmelt runoff water. So perhaps a tillage treatment to incorporate that residue into the surface soil may limit some of those losses. The third treatment is a variable rate fertilizer application. The idea is to have a reduced nitrogen and phosphorus application rate compared to the control, as we do recognize that these basins tend to be high in residual nutrients from a history of fertilizer applications coupled with relatively poor crop removal. And then finally, an annual forage mixture. The idea is to promote infiltration of runoff water from this variable rooting architecture of forages and therefore limit loss or minimize runoff. And within each of these basins, I took a sampling approach to capture 3 unique landform complex positions, the upslope, midslope, and depression. So to understand, how these management practices are performing across the various landscape positions. So we have these calibrated weirs installed at the location where the surface ditch exits each of the channels, where we can measure runoff water and grab a sample for nutrient characteristics. So I do want to just explain a little bit this variable rate fertilizer treatment. First of all, this is made possible through partnership with SWOT maps, and they have, as you can see in the middle of the screen, the SWOT. This is the proprietary SWOT map for this site, which is a system of delineating soil management zones. And so this is done by accounting for soil characteristics, electrical conductivity, nutrient characteristics, and then modeling topography throughout the field. And so we have a system of 10 SWOT zones. The assumption is the soil characteristics are within each of these zones are homogeneous, so then we can apply a unique fertilizer rate to each of these. So the prescription is what you can see on the left side of the screen here. So just to walk you through the approach that we took. So for the red zone of zone 1, these are typically your upslope locations, your watershedding locations. They may be low in organic matter, sandy in soil texture. Zone 5 is your field averages, and then the upper zones, the green zones, are the water accumulating portions of the field. They may be saline. If they are groundwater discharge areas, they may be high in residual nutrients. So the approach we took was to increase our fertilizer application rates as we move from the upslope positions to the midslope, and then reduce our fertilizer application rates in these basin areas to try to utilize some of those residual nutrients. So looking now what we saw in terms of the runoff water. So similar to the first study I mentioned, I collected soil slabs across those transective sampling locations. And what we saw from slabs in 2021, we have the different treatments listed across the x-axis, and then soluble reactive inorganic P across the y. We're seeing a significantly reduced concentration from this forage mixture treatment, as well as a trend for reduced concentration for the variable rate fertilizer and the tillage relative to the control. There was no influence of the landform complex position in terms of the concentration in the runoff water. I'm showing a video here of measuring the runoff in the field. I apologize if it does seem a little bit choppy, but just to show the runoff running through this calibrated weir we have installed within the field. Showing the results of the runoff water that were measured then in the field in the spring of 2022, we did see a significant influence of treatment, where we're seeing significantly reduced concentration from the application of the VR fertilizer, tillage, or the forage compared to the control treatment. Jumping ahead to 2022 grain and straw yields, so wheat was the crop of interest in this season for the annual grain crop treatments, and we can see no significant difference of the treatment in yield. So when we think of the VR fertilizer treatment, we're seeing yields comparable to the control, but achieved with reduced fertilizer application rates. In terms of the complex position, we see not a significant influence, but certainly a trend for increased yield as we move from the upslope to the midslope to the low slope position, reflecting the improved soil moisture dynamics and that low slope site. We can do a bit of an economic analysis to compare the performance of the VR treatment to the control. So in 2022, you can see the mean yields and then the phosphorus and nitrogen fertilizer applied relative to the control and the fertilizer costs. So in this instance, we can see that implementation of the variable rate treatment resulted in savings of $52.93 per hectare because of those reduced fertilizer rates. When we look at the snowmelt simulation data from slabs collected in 2022, we have our treatments listed across the x-axis here, and then soluble reactive inorganic P across the y. And we can see, again, a significant influence of the management practice, where we're seeing a significantly reduced concentration in the tillage and the forage mixture treatment compared to the control, as well as a trend for a reduced concentration from that VR fertilizer treatment. And again, not seeing a significant influence of this landform complex position, which is to suggest that when it comes to snowmelt runoff water, there doesn't appear to be as significant influence of landscape or particularly slope in driving those runoff losses and export of nutrients. In terms of what we saw directly from the basins in the spring of 2023 samples, so we have, again, the same treatments listed across the x-axis and then soluble reactive inorganic P across the y. We can see in this instance a significant reduction in the concentration from that VR fertilizer treatment compared to the control. What I'm showing here is mostly just for additional information and context of what we did. So what this figure here is a discharge hydrograph. So what we are plotting is discharge, or the flow rate of runoff water measured through the basin in 15-minute increments over the period of peak runoff in the spring of 2023. And so you can see this typical shape of a discharge hydrograph where we have a peak where discharge is maximized, and then a drop off and some shorter peaks further on in the runoff period. The orange dots represent time periods where I collected runoff water samples for the concentration of nutrients. And ultimately, this is important for calculating the total load of nutrients in the runoff water. So it's important to know both the concentration of the nutrients in the runoff water, but also the amount of runoff water exiting the system. And so what this sort of culminates in is this table that I'm showing here, where we're estimating the amount of phosphorus load from each of the basins. So across the top of the table, we have the 8 basins listed, followed by the treatment that was applied to each of them. A couple of things I want to point out. First of all, this highlighted row here shows the amount of runoff that was measured from each of these basins in millimeters. So you can see it is quite consistent across each of the basins. So when we look at then, if we see that there's relatively consistent runoff across each of the basins, then we can look to the performance of the management practice and understand how that's influencing the total phosphorus load. And this is what we see here. So for the variable rate fertilizer treatment, you can see that we have the lowest estimated phosphorus loads from this treatment compared to any of the others. So one thing to note is if you look at these numbers, we're in the magnitude of grams of phosphorus per hectare. So these are relatively low losses of phosphorus in that runoff water. But the important thing is surface water bodies can respond to very low concentrations of phosphorus in runoff water. In terms of the 2023 grain and straw yield, so this is canola is the crop in this season. We saw in this instance no significant influence of the treatment. However, the highest yields were reported from this variable rate fertilizer treatment, again, despite a reduced nitrogen and phosphorus application rate. And so this time, if we do this economic analysis, similar to what we observed in 2022, we're seeing that, again, we're saving $57.50 by implementing this VR treatment and achieving the highest yields in this instance. And similar to what we've previously observed, no significant influence of the landform complex position. And in terms of final data from this study, this is the snowmelt simulation data from slabs collected in the fall of 2023. Again, we're seeing a trend for a reduced concentration of phosphorus in the runoff water from the VR fertilizer treatment compared to the control, and no influence of the landform complex position. So just to wrap up this study, we see that the variable rate fertilizer application resulted in similar yields to the control despite a reduced nitrogen and phosphorus fertilizer application rate. We saw the concentration of phosphorus in runoff water was significantly influenced by cropping management practice on the soil slabs, and also in the meltwater that was measured in the field from the drained basins. And the estimated phosphorus load was also the lowest in that treatment of the variable rate fertilizer application. So just in closing here, I want to highlight a few other examples of how we're applying some of these technologies to dial in these 4Rs of nutrient stewardship at the field scale. So the first I want to share is a study led by Dr. Jeff Shano, where he was looking at precision manure management at the Livestock and Forage Center of Excellence. So this study included 3 different approaches to fertility. So commercial fertilizer in the bottom left part of the field, we had constant rate of manure and then variable rate manure application. And in this instance, the system was implemented by a 30-foot JBS manure spreader at variable rate. And the VR approach was developed by Nutrient Ag Solutions Echelon system using 16 years of NDVI imagery. Now, the general approach was to, for the least productive, higher slope positions, to increase the manure application rates. Foot slopes received less, depressions received the least, and no manure to the basin centers. So what did Dr. Shano find in this work? Well, there were similar silage barley yields across the different treatment zones of the fertilizer application approaches after 5 years. The variable rate fertilizer, variable rate manure treatment certainly smoothed out the yields and crop uptake across the basin. So really achieving what was set out by the implementation of that prescription. Initially, there was the reduction of manure, so not applying manure to that basin center did not result in a yield penalty, but it did start to show up after 4 years of cropping. So just to highlight the importance of continuous soil sampling to inform the prescription that we're applying. There was a reduced accumulation of available phosphorus and nitrate at these low slope positions from the variable rate manure treatments, which does point to an environmental benefit. And there was observed lower concentrations of phosphorus in the runoff water and lower nitrous oxide emissions from this VR manure treatment. So the bottom line too is to just the importance of keeping the manure out of these sloughs, out of these locations where there is a greater risk of losses. A couple other examples in this instance using the SWOT maps ecosystem as well, looking at split nitrogen applications. So what we have here in this season, we had our urea being applied at the time of seeding in spring, but then going in with a split application in season for variable rate UAN. And you can see the rates varied across the SWOT zones, and it was done by having soil moisture probes installed within the field and then modeling plant available water across the entire field. So to prescribe the UAN rate to match the predicted yield response as a function of the available soil water. And the final example is what I call variable source, which again, in my mind, I consider application of technology from some of these next generation fertilizer with stabilizers on them. So in this instance, we had 2 layers of fertilizer for our nitrogen. One is with urea as the form of nitrogen, and then the second was nitrogen in the form of the polymer-coated ESN. So the idea is to increase the rate of the polymer-coated urea to increase the rate in the zones where we deemed a risk of losses were greater due to the available soil moisture. So in conclusion here, from this work, we saw that lower solubility phosphorus fertilizer forms demonstrated a lower plant availability and yield response, but also lower losses in snowmelt runoff water. And the differences in the performance and the fate of forms observed across the upslope and low slope sites points towards this need for this site-specific phosphorus management. So really driving home what I had indicated in the introduction about why we should care about site-specific phosphorus management. And after 3 seasons, variable rate fertilizer application that accounts for soil and landscape properties shows promise as a strategy to support nutrient use efficiency. So with that, I do want to acknowledge a number of partners who have supported this work, both as collaborators and financially. And in closing, thanks so much for your attention. Please feel free to connect on X or LinkedIn, and I'd be happy to take any questions.
Thanks for that presentation, Blake. That was really good. We have a few questions here for you whenever you're ready.
Yep, ready anytime.
Okay, sounds good. So when you're setting up these like these trials, do you vary the snow depth based on landscape position, since generally snow redistribution can sometimes be shallower at upper slopes compared to lower slopes?
Great question. So I would say as I had indicated in this webinar, really I took kind of two approaches to measuring the phosphorus losses in the runoff water. So one was through the snowmelt simulation experiment, and then the second was actually measuring the runoff in the field. And so for the snowmelt simulation experiment, I have had a consistent amount of snow across all of the different treatments. And I think really the idea is just to limit the variability in terms of that to control the experiment. So just really looking at the function of the source and the placement method. Now that said, where this variable snow cover comes in is in the field when I'm actually measuring the runoff water from the drain basins. And so part of the work that I do in that is prior to snowmelt doing a snow survey so that we can measure the depth and density of snow for the purpose of calculating the snow water equivalent. So yes, certainly it is an important factor. We're capturing that in the field, but not through the snowmelt simulations.
Okay, yeah, makes sense. Awesome. So next question is, would low pH have the same impact on phosphorus availability as high pH?
Yeah, that is a good question. I think if you, well, maybe, I don't know if I can share my screen again, or if that'll be too complicated for me to, oh, yeah, there we go. Thank you for doing that. So what we're gonna do is we're just gonna go back to this figure here that I had showed earlier. And I hope people can see my screen. Please jump in, Tice, if you can't. But we do have this figure of the availability of phosphorus as a function of pH. So as you can see, again, it does peak around pH of 6.5. And if we go on the other end of the pH spectrum, for the low pH soils, pH 5, pH 4, we do indeed see an influence on the availability of phosphorus. So really, the sweet spot is roughly about that pH of 6.5. So the mechanism to, I guess, correct that or see if we can influence it wouldn't be a fertilizer source that has an acidifying effect, as what we saw being effective at the Langham site, but perhaps look into something that could, a liming agent or something that could influence pH. But really good question, and certainly hearing more about, acidic soils, of course, here in Saskatchewan.
Yeah, absolutely. So next question, where can somebody get a polymer coated phosphorus from, or is that even accessible to farmers yet?
Yeah, so great question. So in this instance, I did have access to it just strictly as a pre-commercial product, just for research purposes. I was able to access it through Dr. Jeff Shano's lab. So to my knowledge, I'm not aware of a commercially available polymer-coated map source at this time.
Well, it's coming, that's for sure. So next question is, what are the potential issues you can run into with phosphorus being broadcasted? Because didn't Manitoba have major issues with this?
Right. So I do. So in response to that question, I think Manitoba has been exploring this issue, even for longer than we are in Saskatchewan, and does have some, guidelines in place in terms of, dictating when fertilizers can be applied and that sort of thing. I think there are some challenges, but I think what folks should be focusing on and particularly paying attention to is especially high risk situations. So I know as an example, thinking to the work of my supervisor, Dr. Jeff Shano, who has looked at, nutrient losses in runoff water from cattle feeding areas, where we're seeing that that manure accumulation, can be a significant driver of nutrient losses. And so, that manure on the soil surface being analogous to broadcast nutrient application. So yeah, I think it is certainly a concern and something to be mindful of. Of course, the recommendation for phosphorus management, especially on soils that are deficient in nutrients, is to get that in-soil application to maximize that agronomic benefit. But I also do recognize that there perhaps could be logistical reasons why people may be interested in broadcasting their nutrients.
Yeah, for sure. There's a lot of good research to back up the benefits of banding fertilizer rather than broadcasting. So the next question we had is, how much do you think moisture had influenced the results of this study? If you had higher rainfall throughout the growing season, do you think the results would have been different?
Great question. I think, yes, we would expect likely some different results. We did experience, 3 successive years of drought-like conditions in this study. And I think some of these, site effects, particularly the improved yield response at the low slope site relative to the upslope site, I think that's magnified, of course, in drought-like conditions, right? Because, this low slope site in the midst of drought, just a better soil moisture conditions, better ability to retain some of that soil moisture, yeah, likely having an impact. That said, I do think, we can also have the flip side of this situation as well, where we have flooding conditions as an example. And you can then also think, well, how would that impact yield at a low slope site relative to a water shedding site? So yes, different moisture conditions are likely to have an outcome, but I guess it's not always the same kind of response that we would see as an example in a wet year compared to a series of dry years.
Yeah, absolutely. So next question we had is there anything producers can do to adjust the pH in the field to improve phosphorus availability? And how can producers use pH levels to plan fertility? And would this have a negative impact on other nutrient uptake?
Yeah, great question. So I guess I will share or go back to what we observed in this study here. So this Langham site having the highest pH of the 3 field sites that I was looking at, pH about 7.6. And it did seem that the best yield response was consistently observed from these sulfur containing sources. So again, one of the sources I was looking at is a product that has MAP plus elemental sulfur within the same granule, and that acidifying effect from the oxidation of the elemental sulfur to sulfate appeared to at least translate into a yield response, which is presumably due to that acidifying effect in the rhizosphere. So on high pH soils, I think yes, there is some nutrients that have a reduced availability under that high pH situation. Low pH also has its challenges. Acidic soils, oftentimes this may manifest itself, though, in reduced availability of certain nutrients, but also can be toxicity of certain nutrients as well. And so in that instance, yeah, perhaps looking towards the use of a liming agent to increase the soil pH to mitigate some of these potential toxicity issues that may manifest.
Awesome, thank you for that. Next question we have is, in more normal or wetter conditions, would rock phosphate be available in the first years after application?
Yeah, I think that's a good question. I think we would expect to see increased availability of that rock phosphate even in the first year of application, because of course one of the things that is tying up the availability of that rock phosphate is simply because it may not have dissolved even to begin with. So as we all know, rock phosphate, there can be a range of granule sizes, but especially if it's relatively large granules, under extreme drought conditions, some of that may not have even dissolved to begin with. And so under improved soil moisture conditions, having just better dissolution, improved microbial processes happening, yeah, I would expect greater availability of that rock phosphate.
Yeah, absolutely. It's crazy how much moisture can really have an impact on fertility and their, the outcomes of these studies that are conducted. So, two more questions. Next one is, what can producers to account for different topography zones in the field if they don't have variable rate equipment? A lot of producers want to use best practice on their farm, but it can take years before they can actually upgrade to that level of equipment.
Great question. And I think, there are certainly certain situations where you can implement, a variable rate situation, like by, manually turning on and off your fertilizer as an example, or adjusting your rates. And so I think just one example, and again, I think it's what came out in one of the studies that I'd referenced from Dr. Jeff Shano's work, the idea of keeping nutrients or manure in that situation out of these flue areas, right? So even you wouldn't necessarily need a manure spreader with VR capabilities to shut that application rate off as you're driving close to a slough or something like this. Similarly, when we're thinking of granular fertilizer application, maybe you are able to drive through a low area at the time of seeding, but you anticipate it may be flooded during the growing season. So you could shut off your fertilizer rate if you're not expecting to get much production in that zone anyway, and then to limit losses. So yeah, I think there are things that can be done even just manually without necessarily having the equipment to implement a variable rate approach.
Yeah, for sure. Cost is usually one of the biggest obstacles producers face when it comes to transitioning to variable rate farming. So it's good that there's still things that farmers can do to adopt precision ag even without the most up-to-date equipment. So the last question we have is, what would a level of phosphorus loss in water runoff be that would be alarming to you?
That is an interesting question, and I think it speaks to one of the challenges inherently when we think of phosphorus, and how we need to balance that it's a plant available nutrient. It is critical to life, and often in a lot of situations our soils are deficient in phosphorus, so therefore of course the need for needing to apply phosphorus fertilizers. And on the flip side, recognizing that, phosphorus, very small concentrations of phosphorus in runoff water can potentially adversely impact water quality. So in terms of the question of an alarming rate, offhand, I'm not, I wouldn't be able to provide a number per se, but I think what is important is to think about, are there some of these win-win situations whereby you're maybe able to, by implementing different management systems or approaches to, maximize the crop uptake of those nutrients, and therefore by default limit losses in the runoff water. So I think that's kind of the approach or the message that I would like to put forward is, how can we work towards these win-win situations where you're doing a management practice anyway that's going to have a good agronomic benefit, also an economic benefit, because the nutrients that you're paying good money for aren't being lost from the system. And then we're also seeing a benefit environmentally.
Yeah, absolutely. So that wraps up all the questions we had. So just thanks again, Blake, for that great presentation and for sticking around to answer all these questions. I hope this helped help the people watching this webinar. So I think that wraps up Blake's portion. We'll move on to Lyle's presentation whenever Lyle's ready.
Great. Thanks so much, everyone.
Hi, I showed my, I think I've shared my slides.
Your slides aren't currently visible. Oh, you almost had it. So yeah, just open PowerPoint. Yeah, we can see the slides, but it's not in present mode right now. So
just need to go into presentation mode. Okay.
Yeah, there we go. Perfect.
We're good there?
Yeah, take it away.
And you can hear me and everything's great. Okay.
Yeah, we're all good.
The challenge of many different ways of presenting. Just one moment here. Get this out of the way. Okay. Well, thanks for having me. Very much appreciated to be able to speak today. Speaking to the topic of making for our management fit on farms. Blake did a fantastic job of providing us with some really great research, good science. The presentation that I'm going to provide this morning is more of a bringing research or management ideas to the farm table. Just keeping myself off screen, I believe. Just to introduce myself, Lyle Cowell. I work as the senior agronomist with Nutrien in Canada, and I have my contact information shared here. I share my information, my contact information, because I'm always open to anybody contacting me if you have questions by phone or text or email. And if you choose to want to follow me on Twitter, there's my Twitter account as well. So again, that's my job, is to speak openly on the topic of NPKs fertilizers, and I appreciate the chance to do so in any means. Sustainability is important in agriculture, and in particular, sustainability is important in fertilizer, including fertilizer manufacturing. And I added this particular slide to acknowledge that fertilizer management in terms of 4R practices and protecting the environment is important from start to finish. It's not entirely a focus just on the farmer, but it starts at the point of fertilizer manufacture. So pictures here on the left, the large industrial complex of fertilizer manufacturing site. In this particular case, that's actually an ammonia/urea manufacturing site. And then on the right, an excellent effort. This is at the Nutrien Fort Saskatchewan site, where the previous phosphogypsum stack piles is now a forest. And again, making every effort that we can throughout the chain of fertilizer manufacture to the point of soil application to ensure that good practices protect the environment, protect society, and do so in an economic means. So we're going to talk about 4R practices. And 4R practices, of course, are using fertilizer, using the right source, applying it at the right rate, at the right time, and putting that fertilizer in the right place. And we need to recognize and accept that fertilizer use is not in isolation on a farm. We have to recognize that we need to use fertilizer to its best purpose on the farm in terms of everything that we do to create the best crop yield that we can. But fertilizer can have off-farm impacts to the environment and to society, and we have to understand how we can limit that negative impact if it may occur. For farmers, 4Rs tend to be mostly about economics. We're trying to achieve the maximum yield, produce the greatest income on the farm, and doing so using good practices to improve fertilizer use efficiency. We do want to eliminate loss of phosphorus, or sorry, loss of fertilizer, including phosphorus. We do want to reduce or eliminate losses on an economic scale. Of course, that also impacts improvement to the environment, but it also, one of the primary reasons that a farmer, of course, is interested in following the 4Rs is to both reduce fertilizer losses, because those are at a cost, as well as improve yield. And we have to also accept, actually, are fortunate that there's a lot of overlap in the terms of the goals of 4R fertilizer application. Now, whether you want to see it as a Venn diagram or as a fertilizer triangle, economics, society, environment do have overlap in best practices in terms of 4R management. As an example, if you take a nutrient band, a nitrogen fertilizer subsoil nutrient band, it's the best in terms of economics and fertilizer use efficiency. It's the best in terms of protecting the environment, and it's the best in terms of protecting society. And that is an important point to make with a farmer, is that what a farm does best in terms of fertilizer management tends to be the best for the environment and society as well. There are other reasons, of course, to beyond economics to use for our management. We do live again within society, within the environment, well beyond the farm gate. And if we do not address good fertilizer practices on farms, then we will start to see pressure in terms of regulation or other means to make sure that we do follow good practices. Using good practices right now and into the future, using a 4R type of approach is the best that we can have into the future to keep good farming decisions in the hands of the farmer. My apologies, my slides are not advancing. There we go. Now, looking beyond economics, the impacts of NPKs fertilizer will vary per nutrient. In terms of all fertilizers, there is value in terms of the economy of the farm and improving efficiency of application. But in terms of the environment, nitrogen and phosphorus should have the most focus. Nitrogen can be lost, and in terms of leaching of nitrates to groundwater, and it can be lost as a greenhouse gas and impact the atmosphere and future climate. In terms of phosphorus, as Blake talked about this morning, movement of phosphorus to surface water can lead to eutrophic conditions, which we'll talk about in a moment. In terms of potassium and sulfur, there is very little social or environmental risk in terms of application. So with with potassium and sulfur, the primary focus would be to improve the economy of application and efficiency of application. We need to take a step back again and talk a little bit about the risk beyond the farm gate. Leaching of nitrates and eutrophication due to phosphates. In Western Canada, we have very few restrictions. And in fact, in Canada, we have very few restrictions in terms of fertilizer use on farms. There are jurisdictions in North America that have implemented some restrictions. They're listed, some of them listed here. And they are regulations, rules that are in place and have been in place for many years to sometimes limit rates of fertilizer, sometimes limit application timing of fertilizer, and sometimes to limit how fertilizer can be applied. These, again, if we follow good 4R practices, we will limit the risk of having these decisions taken out of the farm hands. In terms of leaching, leaching of nitrogen is simply the movement of nitrates below the rooting zone. Now, in terms of that definition, of course, the definition of leaching will vary based on the depth of your crop rooting zone. The chance of nitrates leaching below a forage crop is very, very low. Leaching of nitrates below some annual crops might be much higher. So even just the rooting system itself will define if there is a leaching risk. And of course, we can use that knowledge to also mitigate leaching by, if we have nitrates at depth, we can utilize them by simply growing a crop that has deeper roots. It becomes a problem, though, if the groundwater is contaminated and if that groundwater is being utilized for drinking water, and the drinking water for people or for animals. Nitrates interfere with blood oxygen transportation. And so we, again, have to find ways to ensure that this does not occur. Eutrophication is a topic that comes to the front when we talk about phosphorus management, and it does affect both the environment and society. Eutrophication by phosphorus primarily affects surface water, streams, lakes, deltas, estuaries. It's the reason that a lot of our prairie lakes turn green in the summertime. Phosphorus is a limiting nutrient to algal growth in surface water. And if we introduce phosphorus into surface water, algae will then grow. Sometimes these algal blooms can be very rapid and very extensive. And There are a number of reasons that this can become a problem. In the summertime, algae will shade other water plants and reduce the viability of those plants. It may affect the success of other aquatic biology, from tiny organisms up to fish. And it takes very little phosphorus to create this problem. This question was asked to Blake, and somewhat of a suggestion of the risk eutrophication is here. It only takes about 20 micrograms of phosphorus per liter. So 1 pound of P2O5 would then create a problem to 2 million gallons of water. So it is really the amount of phosphorus, maybe not an economic concern to the farmer as such, but it will become a problem to these surface water bodies. In the wintertime, the problem becomes greater in our Western Canadian provinces because ice forms. In winter, the algae die, they float, they sink to the bottom. As the algae decay, oxygen is depleted, and then we see fish kill. And this becomes then a big issue to society and to the environment beyond the economy of the farm. We also have the issue of nitrous oxide emissions and ammonia emissions. Ammonia is not a greenhouse gas, but it can be a factor in air quality. The smell of ammonia, the impact on, especially whether it be from a product like anhydrous ammonia or from ammonia coming from manure application, it does have a societal impact. Nitrous oxide emissions during nitrification and denitrification is an issue in terms of as a greenhouse gas. It is a powerful greenhouse gas, much more so than CO2, and so we need to limit the losses of nitrous oxides. This is an economic reason for the farmer. We don't want to lose nitrogen, no matter how little it may be, and it certainly has both an environmental and societal impact. So with that, understanding that we do need to use 4R practices to limit losses of fertilizer from the soil on a farm, we then should take the next step and bring 4R practices to the farm gate. There's a number of reasons to do this, and it can be beyond actually just good fertilizer practices. We're now in an environment in society that, and frankly in politics, where farmers may gain some payment in terms of using better practices. An example being the off-calf program from the federal government, which is providing some funding to help subsidize better practices on farms on a one-time basis to improve 4R practices. Right now and into the future, there'll probably be instances and examples of using 4R practices to gain better market access for our crops. And right now, there are carbon offset markets. If we can reduce, for example, our nitrous oxide emissions from a farm using 4R practices, a farmer can in fact be paid for their carbon offsets. And an important point in doing this is accepting that we can do things better on a farm. We often, especially on social media, we'll often see the idea or statements that farmers in Western Canada do everything perfectly, and so why do we need to improve? Yeah, in Western Canada, we do things better than most of the world. We manage fertilizer very, very well. But if you don't try to be better, you're going to become worse. And I fear that we will forget the lessons of history, and in some cases, history not too long ago, where poor fertilizer practices can lead to losses of fertilizer from the field in terms of economy, and then can also affect, again, society and the environment. So this is not a hard concept to take to the farm, just simply using 4R fertilizer plans. To become 4R certified, it's not hard actually. Fertilizer Canada provides a good training modules, and as an aside, these modules will be planned to improve them over the course of the next 6 months, I believe. But if you want to become 4R certified, if you're a PAG, agrologist, or if you're CCA, you simply have to go to the Fertilizer Canada website and take the training to become 4R certified. It takes less than a day, and it provides not all of the answers that you need, but it provides the foundation that you need to understand what 4R practices are. And again, applying 4R to farms, as I say, is a journey, not a stop sign. Not every farm is 100% 4R. We should never assume that it is. And in fact, some of the very best farmers that I've ever known often do not follow full 4R practices for every single nutrient. And that's okay. We shouldn't assume that simply doing a 4R plan means that farmer is 4R compliant in 100% of cases. To me, the value of doing a 4R plan is to improve practices, not to prove that the practices are perfect. And I sometimes see hesitation in people wanting to do 4R plans in the, I'm not the comfort of talking about soil fertility with a farmer. Depending on your background, you may not be comfortable with talking about all the topics of NPKS fertilizer. And that's okay. You don't need to know everything about soil fertility, because 4R plans to me are conversation. They're not based on legislation or any real strict goals in terms of their outcome. It's really about a conversation with the farmer to understand what that farmer is doing on the farm. It's an opportunity for you to learn more about farm fertilizer management, and to then take a step back and learn these topics better. If you have questions that you're not sure about, then you learn about those questions and you become better at them. And what can a 4R plan look like? There's probably many, many different types of 4R plan concepts in Western Canada, depending on who's doing it. I have here an example with the Nutrien logo on it, and it can be very simple. So it's can be a form that you can create that asks the questions on terms of 4Rs for each nutrient. What product are you using? What rate are you using it? And why are you using those rates? When are you applying that fertilizer, and where are you applying that fertilizer, and how are you doing it? And then having that discussion in terms of, are you using the right product at the right rate, applying at the right time? And simply taking these steps forward through each of the nutrients. So you can have a very simple paper or electronic solution to do this for nitrogen, phosphorus, sulfur, potassium. And then in the end, you can have that conversation with the farmer to understand what they can do better. Most farmers already know some of the things that they could do better. Sometimes they'll have questions on how they could do things better. And this is a fantastic opportunity for agronomists to not just understand farms better and fertilizer management better, but to understand soil fertility better. Taking these science topics, such as what Blake talked about this morning, and taking them to the farm gate. The next step that a 4R plan can take is following things like the NERP protocol. And I'm going to just briefly talk about NERP protocols in terms of 4R management for nitrogen. NERP, nitrous oxide reduction protocol, based on practices that were developed by the government of Alberta, provides a framework to best 4R practices for nitrogen fertilizer. The difference between following a NERP protocol and following a basic 4R plan is that in terms of a 4R plan, it's simply a discussion, a conversation about better nitrogen fertilizer practices. And it's a discussion between you and the farmer. You can report your acres to Fertilizer Canada, but they don't have to be proven as such. There's nothing that's going to at this point that has to be proven practices. With the NERP protocol, the books are open. you have to follow the practices and prove that you're following the practices. And why then follow the NERC protocol of the government of Alberta is because the standards of following a program like this is that it has to be based on science and it has to be a program developed by government. So this prevents anybody just deciding what their own plan should be. Take a step back. Why do we always talk about carbon? Carbon dioxide is simply the basis to which we measure emissions. So the NERC protocol, of course, is all about reducing nitrous oxide emissions, and then we will talk about applying those to carbon emissions or carbon credits. It's simply, carbon dioxide is simply the base foundation that we understand emissions, and we will then apply the equivalent amount of nitrous oxide emission or methane emission to equivalency in carbon dioxide emissions. And we see in the farm landscape, there's lots of opportunity that we can lose methane, carbon dioxide, and nitrous oxide. And lots of opportunity then to reduce those emissions. And that may be, and I want to emphasize that this is for all nutrients. You see the manure on the left-hand side here where we will have emissions of methane, nitrous oxide, and as well as carbon dioxide as it decomposes. So there's 3 means of greenhouse gas emissions from improperly applied manure. And fertilizer, there are certainly nitrogen fertilizer, there's certainly emission potential as nitrous oxides. And in the end, these are all brought back to the equivalency of carbon dioxide emissions. I talked about creating a 4R plan through a basic plan. We're sitting down with the farmer and going through their practices. When you bring this to a 4R carbon value, you have to prove the value. And there are basic steps within the NERC protocol that increase the estimated loss of emissions by nitrous oxide. So, for example, a basic level, you would before our practices, which would say that you're using fertilizer in terms of urea, ESN, ammonia, UAN, essentially any of the nitrogen fertilizers available in Western Canada. You are using a soil test or a nitrogen balance calculation to estimate the correct rate of nitrogen applied. In case of a basic plan, the fertilizer rate wouldn't be varied. It would have to be in a subsurface band, and no more than 1/3 of the nitrogen could be top dressed after planting. The top dressing primarily focused being there for farmers who grow potatoes or corn under irrigation, for example. So at the very basic level of a 4R plan in terms of NERC protocol is the nitrogen must be banded. And it must be based on a rate that is determined by either a soil test or an N balance. We can then increase the level of 4R planning and therefore the improved reduction of nitrous oxide emission risk, and then the improved potential for that farmer to be paid for their reduction of emissions by taking the next steps. So an intermediate level of application would be to start to use EEFs in terms of products like nitrification inhibitors, ESN, products like that in high moisture areas, using variable rate nitrogen application. This brings you to the next level of improved reduction in emissions, much like Blake talked about this morning in terms of you can reduce phosphorus losses simply by using variable rate applications. And we can do this for any nutrient. And so we can take these steps, then again, take the basic 4R plans upward in terms of better management to the point that a farmer's emission levels will be very minimal from a field. So let's just talk just briefly then about the 4R plans in terms of the nutrients and some examples on how they can be applied. So first of all, the first 4R is right rate, and it's probably the most difficult 4R to get right. The other 3 R's, the right product, putting them in the right place, applied at the right time, generally we have a good understanding of those. The right rate continues to be a difficult question to answer. Now we can base the right rate of nitrogen fertilizer for any given crop based on past experience. It might be based on soil tests. You might base it on removal rates of nutrients. We do have the new tool, the Prairie Nutrient Calculator. The web link is on the slide. And these are the steps then we can take to find the right rate. Finding that right rate is difficult, but guessing the right rate is not the right way to do things. What is not 4R, again, sometimes it's better to understand not just what is 4R, but what is not 4R. But what is not 4R is applying fertilizer with no guidance or excessive rates. So if the price of canola is $30 a bushel and you decide to apply 300 pounds of N on a field just to make sure that you maximize your yield, that is not 4R. You have to base your right rate on soil tests, removal rates, or some good discussion in terms of finding that right rate. As I said, this is difficult, but then we just can take a step back in finding the right rate. If we can just start to understand the nitrogen cycle, for example, and think about the nitrogen in the soil as somewhat as a bank. We add fertilizer, we add manures, we use legumes to add nitrogen to the soil through nitrogen fixation. These are our additions to that bank of nitrogen in the soil. We remove nitrogen from the soil. And again, shout out to the Prairie Nutrient Calculator with the website there. This is a fantastic new tool that provides us some accurate measurement of rate of removal of nitrogen from the soil. The difficult part of understanding right rate is understanding the reserves within the soil. So we can certainly measure the amount of nitrogen being added. We now, with the Prairie Nutrient Calculator, have good data to understand how much is being removed. We still have some work to do in understanding the reserves of nitrogen in the soil in terms of how much nitrogen is there and how fast that nitrogen becomes available to the crop. We use soil tests, and we should always use soil tests wherever possible. But that is probably our greatest limitation in terms of right rate. In terms of right time, again, focusing on nitrogen here, but just some examples with other nutrients. Right time is going to be somewhat based on the mobility of the nutrient. So nitrates and sulfates are quite mobile. Potassium and phosphates are quite immobile. We then have a wider range of potential for the system to be leaky. So nitrogen may leak out of the system because of the mobility of nitrogen, whereas potassium as a fairly non-mobile cation that will be adsorbed to clay and organic matter, it has quite low mobility. So we then can take these understanding of basic soil fertility to understanding the right time of application. Because potassium and phosphorus are quite immobile, that is why one of the reasons, the primary reasons, that we should try to find ways of applying phosphorus and potassium near the root system of our annual crops, because they begin life with very small root systems, and so we need to have that phosphorus and potassium within those small seedling root system. Whereas nitrogen and sulfur, as nitrates and sulfates, have a little bit more flexibility. This is where we can apply nitrogen and sulfur well ahead of seeding and still have good efficiency. Now, what is not 4R again? What is not 4R again in terms of nitrogen fertilizer application is applying nitrogen in winter, or application of all of your fertilizer after emergence. we still see nitrogen fertilizer being applied in wintertime in Saskatchewan, and that is very not 4R. And so these are the sort of examples that we have to take to the farm, because a farmer applying nitrogen in winter is using that nitrogen inefficiently, so the economy of 4Rs is poor, plus there is an impact, potential impact on society and the environment. A good point to understand in terms of right time too is, when do crops need nutrients? And by and large, crops, especially our short season annual crops in Western Canada, canola, wheat, barley, and so on, we are trying to grow these crops to physiological maturity often within 90 days. And on top of that, crops accumulate nutrients much faster than they accumulate dry matter. So we need to have the NPKS fertilizer in particular applied very early in the season. How soon is too soon? Well, as I said, because of mobility, it doesn't make a lot of sense to apply phosphorus or potassium well ahead of seeding. In the case of potassium, because of its low risk of loss, it may make sense if you broadcast potassium. There's low risk to loss, and sometimes this can make sense. So it just depends on the farm management. Fall application of phosphorus or surface application of phosphorus in Western Canada simply doesn't make sense. Now, in the case of nutrients like nitrogen and sulfur, earlier application can work out. So some nice data here from Regis Karamanos, worked out of Waterous and Lake Lenore, demonstrating that proper fall application of nitrogen can be efficient. So this data indicated that application of nitrogen in fall was as efficient as nitrogen application in spring. Now, we still have to follow good management practices in fall. We still need to ban the nitrogen fertilizer, because if you don't, that's not 4R. And we should apply the nitrogen fertilizer, if we do it in fall, when the soils are cool, because we are trying to reduce the risk of nitrification and then subsequent losses of nitrogen as nitrates or as nitrous gases. Right place, talking about the various nutrients as well. Again, the low mobility of nutrients like phosphorus and potassium, as we already discussed, need to be applied near the seed row. The right place for nitrogen is in a band. We've talked about this already, and it's the efficiency of nitrogen in a band is almost always significantly higher than broadcast nitrogen, and for a number of reasons. Surface applied nitrogen can be lost as a gas. It could be lost by erosion. It's more likely to be gained and taken up by weeds. And on top of that, nitrogen that is applied with residue is more likely to be immobilized by bacteria during residue decay. And so the efficiency of that nitrogen fertilizer becomes lower when it is broadcast. And this has been proven for decades. This is work summarizing only up to 1993, I believe it is, 106 site years of data indicating the improved 4R efficiency of banding nitrogen fertilizer versus broadcasting nitrogen fertilizer. A lot of data was accumulated through the 1980s and 1990s to understand banding versus broadcasting of nitrogen fertilizer, because that is in the era that we gained the equipment to be able to band nitrogen fertilizer. So that's where a lot of our data bank comes from. And in 106 site years of data in Western Canada during that time period, it was proven that nitrogen fertilizer in a band, total efficiency almost 30% higher than broadcast. And in terms of yield, the average yield increase was about 15% greater. Right product really, I think, is fairly well established for Western Canada. Again, it does depend on the other 3 Rs. An excellent example would be elemental sulfur fertilizer. Now, we know that crops need sulfur in a sulfate form to be utilized. So can elemental sulfur fertilizer be used as a right product? It can be if you use the other 3 R's, and understanding that it takes some time for that sulfur to oxidize to an available form. Applying elemental sulfur fertilizer at the time of seeding and expecting it to fully provide sufficient sulfur to a crop in a deficient soil, that's not following good 4R practices. Managing elemental sulfur as a residual fertilizer to provide sulfur over the course of rotations, that can be a 4R practice. So it just depends, again, how you manage the product in terms of the other 3 right practices. It kind of comes down to simply sitting down again with the farmer to understand the risk of loss and finding all those points to reduce the risk of loss. So for another example, products, specialty products. We have urea, but the specialty products using things like ESN or adding agrotane, NBPT to urea. Again, it depends on the other 3 R's. Are you using these products for questions as are on the bottom? I'd like to reduce the risk of losses of nitrogen fertilizer. I'd like to delay the availability of urea to improve protein in my wheat crop. I'd like to apply nitrogen in a band at the time of seeding and reduce risk of injury to the seed. So some of these specialty products, you'll have to ask these other questions to understand if they fit within a 4R management plan. I'm just going to go through an example, a couple examples actually, and just set the stage to how we can approach a farmer and talk about practices on the farm. I'm not going to create a 4R plan by any means. That would take us another hour, but just a couple examples of where we can sit down with the farmer and better understand practices. So Farmer Stacy has asked you to review her farm's fertilizer plans and complete a 4R plan with her. Stacy grows wheat and canola in rotation with peas. The peas on about 5 to 10% of her acres, 4,000 acre farm, farms with her husband, who is a veterinarian and having a cow calf operation. And we have to know that there's cattle, so there's going to be manure, and manure provides nutrients. Well, I've got Stacy living in Peace River, Alberta, but we can pretend that Stacy's living at Meadow Lake today. What else do you want to add, Stacy? We need to ask these questions to provide the general understanding of how the farm is managed, but then we need to know some more details. Well, we need to know how fertilizer is applied and how Stacy seeds. So Stacy seeds with a Borgo drill using mid-row banders, yield goals of 50 bushels per acre of canola and 60 bushels per acre of wheat. And Stacy has been applying 120 pounds of nitrogen as ammonia for both crops, has been applying 30 pounds of phosphorus for both crops, has been broadcasting 100 pounds of ammonium sulfate before canola crops, and has been inoculating the peas and applying about 15 pounds of phosphorus with those peas in the seed row. Her 10-year average yield has been 45 bushels per acre for canola and 50 for wheat. So not achieving the goals, still good yields, but not achieving the goals, which is not an uncommon issue in terms of finding the right rates of fertilizer. We often have higher yield goals than what we often achieve. And then, as I said, there's cattle. So they spread the manure, what they consider the poorer areas of the field. But Stacy noted, and a concern to her is that they've been applying the manure, but it doesn't seem to be really helping yield much. So let's just take a step back and let's look at removal. We've got the nutrient removal calculator with the prairie nutrient removal project. And let's look at the balance. So starting off with canola, the goal is 50 bushels an acre, actually achieving 45 bushels per acre. If achieving the goal, the removal rate would be 94 pounds of nitrogen, 39 pounds of phosphorus, and so on for potassium and sulfur, compared to the actual removal. Now, Stacy's been applying pretty high rates of fertilizer, 120 pounds of nitrogen as ammonia, plus there's nitrogen in the phosphorus, there's nitrogen that comes with the ammonium sulfate. So Stacy's actually been applying 140 pounds of N per acre, well above what her either would match to her actual yields or her yield goals. The phosphorus rate, she's actually been applying a little bit less than actual removal rates, and so on for potassium and sulfur. We start to see these balances between nutrients, and we can do the same thing with wheat. The goal being 60 bushels per acre, the the actual average yield having been 50. Stacy's been applying 120 pounds of nitrogen again on her wheat, but removing substantially less. The phosphorus rate of application has been close to matching what her removal rate is. In terms of potassium, this is something that we have to consider. Stacy is applying 0 potassium on any of the crops, but is removing potassium each year. And so that might be a concern. It's something that should be highlighted as an imbalance in application if soil tests prove that the potassium levels are low. Now, Stacy's not applying sulfur on her wheat, and actually she's assuming that her high rate of sulfur application with the canola will provide residual sulfur. And the peas, a similar sort of exercise, assuming that the nitrogen the peas fix their own nitrogen, so offsets the nitrogen removal, and so on through the nutrients. Applying very little fertilizer to the peas and possibly underestimating the removal rate, in particular for phosphorus and potassium. Now, Stacy has pretty good land, but we know that in Western Canada that every farm has some marginal land. And she's not really sure if she's spending her dollar well on fertilizer. Here's an example of a field. And this is, Blake showed images of using variable rate applications and NDVI imagery and so on earlier today. This is another example of using imagery at hand that we have in today's farming practices to improve fertilizer nutrient application. So here's the imagery. We see very clearly by a drone image as well as by this imagery that the low yield shows up very clearly within this field. Now, she has a soil test, a composite of the whole field. What do we see here? Well, okay, so the pH is probably not a problem. It's a non-saline, generally non-saline, certainly not enough salinity there to impact yield. The organic matter is fairly high. There seems to be fairly high residual nitrates, remembering that she's applying more nitrogen that she's removing. This phosphorus level on the whole field is actually quite high, and as is the potassium level it's marginal. The potassium level is fairly low, and very high levels of sulfur in the composite soil test. So here's some things to talk about. Well, there's probably applying a little bit more nitrogen than required, because we do see some residual nitrogen here after the crop. High levels of phosphorus in the soil. Where is that coming from? Well, it's a composite of the field. We know that Stacy has been applying manure, and in particular applying manure in some of the poor parts of the field. And we have probably essentially contaminated our soil sample by taking samples from the field from where manure has been applied. So let's take a step back with Stacy. I think we need to separate this field and sample the good areas versus the bad areas at very least to understand what the phosphorus requirement of this field really is. And the same would be true for the potassium and sulfur. Now, the potassium level is marginal. There's probably a good chance that this field might have some potassium deficient areas within the field. And so again, splitting this field, sampling it separately, at least taking splitting it to 2 different areas would be of benefit. And the sulfate's very high. Well, again, this might be due to a few things. It might be due to the relatively high rates of ammonium sulfate application. We do see that there is possibly a little bit of salinity in this field too. Not enough to impact yields, but certainly enough to impact sulfate levels in the field. So the soil test starts to give us a lot of clues, and even though Stacy has been managing her field very, very well, we see some points here where maybe we can improve practices. So we go back and resample the field. And what do we see here? Well, the pore area, it's not due to salinity. The saline area is actually has very, very low conductivity. The nitrates are quite high. And why was that? Why would that be? Because Stacy is applying a blanket rate of nitrogen across the entire field, even though there are low yielding areas of the field. So probably a good step here would be to start varying nitrogen rates. She's been applying manure on the poor areas of the field, and it shows up very clearly here in the high levels of phosphorus in the poor areas, phosphorus from the manure. The potassium levels are quite low in the poor areas. Sulfate levels are quite high. So the problem is not due to sulfur. We might have a potassium deficiency here. And when we scan through the micronutrients, you see copper at 0.4 ppm, that Stacy might be in an area where it might be both potassium responsive and copper responsive. A low yielding area of the field, probably quite sandy, low organic matter. We now can take some steps on understanding her soil and her farm fertilizer practices. Again, even though Stacy has been doing what on the outside looks like an exceptionally good job of managing her farm, we can find some steps to improve yields and economy and do better things for the environment. And then we just step back and go through this very simple farm plan for our plan with Stacy, talking about nitrogen rates, phosphorus, potassium, and sulfur rates, and then having that conversation to how we can improve practices on the farm. And Stacy, although we know that she has done a very good job of managing her fertilizer, is willing to improve practices, and that's to the benefit of everybody involved. One more quick scenario. I think we have time. We'll just quickly go through this. Farmer Doug has asked you again, much like Stacy, to review his farm plans and come up with a 4R plan. Doug farms near Dundurn, farms growing primarily durum wheat and lentils, and once in a while includes canola in the rotation. Seeds with a seed hawk, dual shanks, targets 40 bushels an acre for wheat and 25 for lentils, applies 50 pounds of N in a blend of urea and ESN, applies a relatively low rate of phosphorus, as 1152 to the wheat and lentils. He does inoculate the lentils, which is good to know, and he does grow some canola, but he uses the same rate of nitrogen phosphorus for wheat, so he doesn't want to have more than one blend, and he throws in an extra 10 pounds of sulfur as elemental sulfur into that blend for the canola. There's his long-term averages, not too bad for durum, actually not too bad for lentils, a little bit low for canola. So again, a very typical farmer following quite good practices, but can Doug improve his 4R practices? This is his home quarter. What do we see here? We have a drone image and we have a NDVI image. We can quickly start to see the areas that produce very well and the areas that produce very poorly. We have some clues here on Doug's home quarter to what there might be some problems. There's very obviously some kochia patches and some salinity, which we would see whether we're walking across the field or we use drone images. So the poor area, we've gone out and let's sort out what's wrong with the poor area. Well, again, the pH is not a problem, but we see that in fact the poor area is quite saline, both on the surface and subsoil. There are significant residual level of nitrogen in these areas, residual phosphorus, potassium levels quite high, the sulfur level is very high, and this is all being driven by salinity. The micronutrient levels are all quite high. So these saline areas although we are following this plan as a 4R nutrient plan, the soil test is telling us that the problem is not so much a nutrient deficiency, but a problem in terms of yield variability. And in this case, salinity, which is reducing yield potential. And because Doug has been applying blanket rates of NPKs fertilizer across the field, There's significant residual levels of nitrates and phosphorus and potassium, and the very high level of sulfur here entirely being driven by the sulfate salts due to salinity. There are no micronutrient deficiency risks based on these soil tests, and so our 4R plan here is not to apply more fertilizer in a given area, but to understand that the low yield potential here will actually should be addressed by applying less nutrients in the most suboptimal areas, and probably could achieve better yields by simply moving some of that fertilizer to the better yielding parts of the field. So that's my slides. Again, I want to thank the opportunity to talk about 4R planning. If anything that I would hope that comes out of this is to take any concern or fear people might have towards sitting down with a farmer at your desk or at the farmer's desk and creating a good 4R plan. It's important to be able to have that comfort level to be able to do so. If we start doing this with every farmer, we will find better fertilizer practices. It'll improve the economy of Saskatchewan farms. It'll reduce the risk to society and to the environment. And everybody wins when we follow these good 4R plans. That concludes my slides. I'm not sure if there's any questions.
Thank you, Lyle, for that awesome presentation. It was actually really cool how you included those case studies, hands-on, real real world approaches to 4R situations. So that was really good. I really like that. So we have a few questions here for you.
Sure.
The first one is, over time, zero tillage practices have resulted in the acidification of fertilizer ban due to the addition of acidifying NH3 sources. This has, for example, had the potential to decrease sulfur availability and increase the potential for aluminum toxicity. How likely do you see this potential of occurring?
Sure. I'm just going to take the risk and putting my camera on here. If I start to lag too much, just let me know and I'll take the camera off.
Mm-hmm.
Okay, so acidification with fertilizer application, and we shouldn't just say fertilizer application. So acidification primarily will come with ammonium fertilizers and with elemental sulfur. Those are the two primary fertilizers that will lead to acidification. So, for example, so the risk is actually higher for ammonium fertilizer than it would be for ammonia fertilizer. It's just the way it is. And it is a risk. And this is also the case with all nutrients that we apply to land, including manure nutrients. And is there a long-term risk to Western Canada? Not to any great extent. A significant portion of Western Canada, to be very honest, probably benefits a little bit from slightly lower pH. If you are starting off with acidic soils, poorly buffered acidic soils, so if you have an acidic sandy soil with low organic matter, pH of say under 5.5, this can become a long-term risk. And the solution then, not a common practice, eventually we might have to find solutions for some of these acidic soils. That might be liming. In some cases, it might be choosing different crops that can tolerate some level of acidity. And in some cases, some of our most acidic soils along in Saskatchewan are pretty marginal soils, low organic matter sandy soils, and sometimes in terms of acidity as well as a lot of other reasons that soils can be marginal. Sometimes we have to accept that some land is better off in forest and forage. Now, there is a little bit of benefit in some soils. If you have a highly carbonated, high pH soil with a pH of 7.5 and a lot of free lime within it, having some level of acidity within the fertilizer band is actually a benefit. And that's actually one of the primary reasons why monoammonium phosphate 1152 is a better phosphorus fertilizer for most of our soils. As Blake demonstrated this morning, that bit of acidification, be it from the ammonium or in some cases if there's sulfur within the product, that can actually improve phosphorus uptake and availability and uptake. So it's a balance, and it'll depend on which soil that you're dealing with. Big picture for Saskatchewan, significant soil acidification is not going to be a significant issue for most of our soils. It'll become a problem well beyond when we have other problems for our soil. Top of mind, things like availability of phosphorus and that sort of thing. So certainly an issue, certainly important. And one other, and I'm sorry I'm dragging this out, but sometimes we limit our thinking about a soil acidity in terms of crop potential, but we do have to remember the soil pH also affects availability of nutrients, affects the activity of some soil applied herbicides, and the impact on some diseases such as aphanomyces or clubroot. So soil pH within itself is a bigger topic than just availability, the direct impact on crops.
Yeah, absolutely, for sure. So the next question I have is from an agronomist who has taken the 4R training online but hasn't had like a 4R plan with a grower yet. What advice can you give to them when they go into their first meeting with a grower about 4R planning?
See it as a learning exercise. See it as a learning exercise for yourself and the farmer. Farmers like to talk about how they grow crops. And the only concern I've ever heard from farmers in doing a 4R plan is, what are you going to do with what you just, I gave you my records, now what are you going to do with them? A basic 4R plan can be just between you and the farmer. When you report 4R acres, you simply report that a plan has been made. And be very honest. I always make the assumption that when I do a 4R plan and report it through Fertilizer Canada, I make the assumption that I've done a plan with the farmer. That doesn't mean that everything that on the farm is being done 100% with 4R practices. The goal is to do things better, to not do things perfectly. So in the end, understand what the basic 4R questions are. Ask about the right product, the place, the time, and the rate of that fertilizer application. Understand how it's being applied through the equipment. And the best advice I still think that can be taken is to see this as an opportunity to learn yourself. Because the farmer might ask you questions, much as I might have questions this morning about, I'm applying this fertilizer, how does that affect other conditions within my soil? You might not know that answer. And I still am not afraid to say, I don't know, and find an answer in the future. Don't go to a farm table and with the expectation that you are going to tell a farmer that farmer is doing things right or wrong. There are not two farmers that farm the same in Western Canada, and yet there's lots of farmers that do things really, really well. So just again, this is a learning opportunity for both yourself and the farmer. And be prepared to discover things on that farm that you didn't expect the farmer was doing. That might be doing some practices that are not very good, and you can help find a better practice.
For sure, yeah. 4R is it's a fairly new concept to a lot of us, and implementing it widespread, it's going to be part of the journey for crop production in Saskatchewan over the next decade. So yeah, no, it's definitely a learning experience for all of us. So that's definitely important to keep in mind. Thank you for that. So next question we have is from another agronomist. He asks, what is the best approach to convince farmers to have a 4R plan, that having a 4R plan on their farm is worth it? And then second question is, what has been your best experience with getting farmers interested in 4R?
Why is it important? The first response that comes to mind is the wrong one. So there's two reasons, and here's what shouldn't be the priority. The priority of the farmer shouldn't be to create a record because they assume that someone's going to be telling them how to farm in the future. You should have records. I mean, and a farm should keep records of practices, but they should be for agronomy reasons. And so really the reason to sit down and do a 4R plan is to improve the economy of production on the farm and better use of fertilizer. In most cases, it does not mean a reduction in fertilizer use. It means better fertilizer use efficiency. So we're really doing this for the betterment of the economy. And remember to the farmer that one of the 4Rs is economy. And none of the 4Rs come together unless all of those pieces of the puzzle fit together. And one of those needs to be economy. So any 4R practice that is recommended is also to the betterment of the success of a farm. That's very important. How do you get a farmer interested in wanting to do this? You know, again, I think that if you present it that way, in terms of just showing that you want to understand their practices on their farm, and not to tell them how to do things, but to understand how things are done, and then create an environment where you can work together to improve fertilizer practices, that's the way to approach it. This is not a legislated requirement. There are not strict rules around exactly what a 4R plan should look like. Again, we do not spend nearly enough time at farm tables or at your desk with a farmer talking about fertilizer management. As someone who spends his life and cares so deeply about NPKs fertilizer, we spend more time at farm tables talking about which fungicide they use than we do with all of NPKs fertilizer, and yet NPKs fertilizer is probably 60 to 70% of the cost on that farm. And so don't underestimate the importance of having that conversation. It's as important or more important than anything else the farmer is going to talk to you about.
Yeah, for sure, absolutely. Thank you for that. So next question we have is the three-parter actually. So Manitoba got to the point where they had to place regulations on fertilizer use in the province. Number one, do you see benefit to this? Number two, do you think Saskatchewan producers could have widespread adoption of 4R practices without regulations? And number three, how can we continue to encourage these practices with growers to avoid this?
Yeah, so there's some pretty light restrictions in Manitoba. There's some restrictions on, and understanding I'm not in Manitoba, so I'm speaking outside the boundaries of them. But there are some restrictions in terms of when you can apply fertilizer in the fall, for example. There'll be a cutoff date in Manitoba to when they do not want to see fertilizer applied. It is very rare for that to actually have a restriction on actually the amount of fertilizer applied. And there are certain other rules, especially around manures, as far as having fertilizer management plans, essentially 4R plans around manure application. That's not a bad thing. Again, the real intention is to improve efficiency of nutrients. Do we need to be legislated to do this in Saskatchewan? I don't think so. I hope that good practices and good economy on farms drive the right practices. Sometimes it doesn't. As long as we are still having a conversation in Saskatchewan about broadcasting urea on snow, we're a long ways away from doing everything right. This is a practice that was proven to be a poor practice 40 years ago, and yet we still see it happen. 4R nitrogen application is in a band, and so the gain for the farmer is economy and better yields, reduced losses, better efficiency of the nitrogen fertilizer, and better yields. And I think that simply understanding what is 4R, but also what is not 4R. And sometimes I think that we need to understand what is not a 4R practice to bring that home to the farm gate, and why it is not a 4R practice. And those are the primary steps that I think we need to avoid the need to have legislative control of fertilizer application. I don't know if there's three questions. I don't know if I answered them, but.
Yeah, no, I think that's a good answer for that question. Hopefully it doesn't get to the point where legislation has to get involved. Hopefully farmers can cooperate and adopt 4R practices while maintaining high yields and profitability. So next question we have is what type of testing is available for manure to actually see what nutrients you're all applying with it?
Yeah, that's a tricky one. I mean, you can take samples of manure, and it's difficult to get good samples of manure. But you can send samples to, I'm quite speaking outside the box here a little bit, but I'm pretty sure that any of the soil test labs do manure analysis. You can, the problem with this is that you can analyze the amount of nutrients in manure, and that's well established in terms of methodology. The trick will be the application rates and trying to estimate the actual availability of those nutrients to the crop, because it's much less predictable than a synthetic mineral fertilizer. That being said, manures are a fantastic resource, and if utilized properly, can be a very, very valuable nutrient resource. So yes, contact your local soil test lab. They'll be able to do the analysis and probably provide some estimation of the availability of the nutrients within that manure. It comes down, the biggest problem is probably with manures is the non-uniformity of application.
Yeah, absolutely. It's definitely important to know what you're dealing with.
Yep.
So next question we have is, what level of residual phosphorus would you consider too much for it to risk losing some of it to runoff?
Blake probably could answer this a lot better than I can. As he demonstrated, and in what we know for our soils in Western Canada, the risk, it depends on the question. So the risk of an economic, and Blake had this question, and I think I addressed it in one of the slides, the amount of phosphorus lost from a field through runoff, and this can be by actual physical soil runoff, where the soil is being channeled into rills or gullies and actually physically being lost, or loss of soluble phosphorus. Water moving through decayed residue and taking with it soluble phosphorus. The amount tends to be very small, largely because in Western Canada we have adopted the equipment and methods to band apply phosphorus fertilizer under the ground. In regions where phosphorus, and I want to make a good point that we are unique in applying phosphorus in subsoil bands in the world. There's not many regions in the world do this, and it is the best, most efficient way that you can apply phosphorus. A lot of the world broadcasts phosphorus, and then they have not just soluble losses of soluble organic compounds, but also just direct runoff of phosphorus. And this is where we caught in the flood, in a sense. Phosphorus runoff by other means, within other regions and reaching into the Mississippi River and the Chesapeake Bay or into the Great Lakes and so on. That becomes a huge problem because society creates focus on phosphorus runoff, even if in Western Canada the amount of loss is very, very low. So economically in Western Canada our losses are very, very low. That doesn't mean to say that we shouldn't try to reduce losses, because again, water quality takes very little phosphorus moving into surface water to create a problem. And whether you live in the farm or you live in the city, we don't want to see algal blooms. It's a problem. So, and we can limit this again by subsoil banding of phosphorus, as we do most of the time in Western Canada at the time of seeding. Manure applications, if we can keep those manure applications away from water bodies or runoff channels, and even better, especially in terms of liquid manure, subsurface banded, it's just going to be better. So we need to take all of these steps to reduce risk of losses. So the economic risk to the farmer is small, the risk to society and environment is much greater.
Yeah, absolutely. So we have 3 more questions. I just want to say I apologize that we're going a little bit over time. So if any of you need to jump off and haven't received your CCA or your CCA credits yet, we just reach out to either Ali Noble or Ashley Kaminsky, and you'll be able to get those credits if you have to jump off. If not, then we'll ask these 3 questions and then hand out the credit. So next question we have is, should we aim to put nutrients in and pull them out at a 1-to-1 ratio? For example, with nitrogen, if you have a bit left over from the previous year, should you be dropping nitrogen rates for this year? And then because their reasoning is it's better to have a little extra nitrogen in the soil rather than not enough. What are your thoughts with that?
Yeah, I don't disagree. We just don't want to get carried away with this. A little bit of residual N can be a benefit to crop production. Excessive levels of residual N can be a problem. Should we apply it in a 1-to-1 ratio? That just depends, especially with nitrogen. It's probably the balance we can probably get pretty close to a balance. And if you actually look at average nutrient removal rates by crops in Western Canada compared to the average rate of nitrogen in Western Canada, we're actually pretty close to being in balance. It's going to vary by, so in terms of Western Canada, our balance is there. The question is, are we in balance on every farm or every field or every part of field? So this is where we can start to make better management practices and making sure that, use variable rate nitrogen fertilizer. That will ensure that there's less residual N on your marginal land, and we can move some of that nitrogen to our better land and overall have less residual nitrogen because we have better use in the best land and less residual N in the poor land. Very, very simple steps, very simple concepts. So we can take better steps to achieve that 1-to-1 ratio of removal versus application without affecting, and in fact, I would say not only not affecting yield, but improving yields and reducing risk of losses to the environment. Because if we apply nitrogen where it's needed, there's going to be less loss.
Yeah, absolutely. So next question we have is, how can we implement strategies to reduce soil acidification by adding, for example, by adding gypsum or lime-based products with humic acid-based products?
Well, first of all, gypsum doesn't affect pH. When you add lime, calcium carbonate, it is not the calcium that impacts soil pH, it is the carbonate. Calcium itself will have a neutral reaction within the soil, and sulfate itself is a neutral reaction within the soil. Ammonium sulfate is acidifying because of the ammonium, not because of the sulfate. So gypsum has no impact on soil pH. So that's off the table. In addition, effective liming will require probably thousands of pounds of lime per acre to actually overcome what is any meaningful level of acidification within the soil. If you actually have a soil pH that is a problem in terms of pH levels and potential acidification, applying a few pounds per acre is not going to help you. If you're in terms of liming, as my friend in Australia told me, it looks like a bloody snowed, and you have to work it into the soil. Very, very high rates of lime to be really truly effective in terms of liming. So again, gypsum is not going to help you. Lime will help you if utilized properly, and humic acids, you can try them if you want. I'm fairly skeptical in their value in terms of affecting soil chemistry. Remembering that we have humic acid in our soil already before we need to add any more.
Yeah, thank you for your thoughts on that. So last question we have is, how can you estimate the right mineralization rate to estimate nutrients?
Oh man, we've been chasing that golden ticket since I was a young person. We need to get there. We're not getting there very fast. In particular, we've chased mineralization rates of nitrogen for literally decades, and we really haven't gotten anywhere. But we shouldn't limit ourselves to the idea that it is only understanding that nitrogen, significant part of portion of phosphorus can be mineralized as well from residue, as well as sulfur, and we just haven't got there. If Les Henry was listening, maybe he is, he would tell you to leave your soil on the desk for a week and before you send it into the soil test lab. There are lab methodologies that can measure potential mineralization. And I'm confident that in the next 10 years, we will get to a point where we actually have a soil test that is not just a nitrate test, but a nitrate test plus a meaningful mineralization test. I think we can get there. It's a matter of whether we can create the research to support the data and then have labs accept that data or methodology and farmers accept it as a meaningful measure. The first place this has to happen, to be honest, is we need to have the support to do the research to prove the concept. And right now, I don't see it happening. I hope that it does in the future.
Yeah, absolutely. So that wraps up all the questions we have that. So thank you, Lyle, for answering all these questions and for that great presentation today. So next up, we'll get that CCA credit to you guys.
Well, thank you again. Really appreciate good turnout today, and really appreciate the questions. And if